Imagine falling through an atmosphere, and never stopping. No surface. No ground. Just endless ocean, pressing tighter around you, until the water itself becomes something that isn't water anymore. This is not science fiction. This is Neptune. This is Uranus. And this is what we now believe exists on dozens of worlds scattered across our galaxy. You have never stood on solid ground the way you think you have. Earth's crust is a thin shell, barely 40 kilometers deep, floating on a mantle of slow-moving rock. But some planets skip the shell entirely. They are spheres of liquid and gas, wrapped around cores so compressed that physics itself starts to blur. And until 20 years ago, we had no idea how common they were. What would it mean if most planets in the universe have no surface at all? What would it mean for our search for life, for our understanding of what a world even is? By the end of this journey, you will understand exactly why planetary scientists are rewriting the textbooks, and why the answer challenges everything we assumed about where life could exist. The story begins with two ice giants in our own cosmic backyard. Neptune and Uranus have puzzled astronomers since William Herschel spotted Uranus in 1781. For centuries, we called them gas giants, lumping them together with Jupiter and Saturn. But modern observations revealed something profoundly different. These worlds are not mostly gas. They are mostly liquid. Beneath their blue-green atmospheres lies an ocean with no bottom. Descend through the hydrogen and helium clouds, and you encounter water, ammonia, and methane compressed into a supercritical fluid, a state where the distinction between liquid and gas dissolves. Go deeper still, and pressures reach millions of atmospheres. The temperature climbs to thousands of degrees. And somewhere in that crushing darkness, something extraordinary happens. Dr. Burkhard Meili-Zuer, a planetary physicist at UC Berkeley, describes it simply: the chemistry down there does things we cannot replicate in any laboratory on Earth. His team's simulations suggest that at around 7,000 kilometers deep inside Neptune, methane molecules shatter. Carbon atoms, freed from their bonds, begin to link together under unimaginable pressure. They crystallize. They rain downward. Diamonds. Falling like hailstones through an ocean of superheated water. This is not speculation. In 2017, researchers at the SLAC National Accelerator Laboratory recreated these conditions for a fraction of a second. They watched diamond formation happen in real time. The ice giants of our solar system are producing gemstones in quantities that dwarf every diamond ever mined on Earth, and they have been doing it for 4 billion years. But Neptune and Uranus were just the beginning. When NASA's Kepler Space Telescope began surveying distant star systems, it found something no one predicted. The most common type of planet in our galaxy is not a rocky world like Earth. It is not a gas giant like Jupiter. It is something in between, a category we had never seen before, because nothing like it exists in our solar system. Planetary scientists call them sub-Neptunes. Worlds 2 to 4 times Earth's diameter. Too large to be purely rocky. Too small to hold onto massive hydrogen envelopes like Saturn. And the data suggests one stunning conclusion: many of them may be ocean worlds, with liquid layers hundreds or even thousands of kilometers deep, surrounding rocky cores we will never see. Dr. Sarah Seeger, MIT astrophysicist and pioneer in exoplanet atmospheres, puts the numbers in perspective. We have confirmed over 5,000 exoplanets. Sub-Neptunes appear to be the most common. And most of them may have no solid surface whatsoever. Think about that. The universe's most abundant planet type might be a world where you could never land. Where the concept of ground simply does not apply. The James Webb Space Telescope is now turning its infrared eye toward these worlds, searching for water vapor, methane, and ammonia in their atmospheres, the chemical fingerprints of vast liquid interiors. What it finds could reshape our understanding of planetary formation. And it raises a question that haunts astrobiologists: could life exist on a world with no floor to stand on? But before we can answer that, we need to understand how these impossible planets form in the first place. For most of human history, we assumed every world had a surface. The moon had craters you could walk across. Mars had deserts that rovers could explore. Even the sun, ancient astronomers believed, might hide solid ground beneath its flames. The idea that a planet could be liquid all the way through, that possibility never entered the scientific imagination. Then we sent spacecraft to Jupiter. In 1973, Pioneer 10 became the first probe to cross the asteroid belt and approach the gas giant. What it found forced astronomers to abandon centuries of assumptions. Jupiter had no surface. Its atmosphere simply grew denser and hotter as you descended, until the hydrogen gas gradually transitioned into a liquid state. There was no boundary. No splash. Just a slow, terrifying compression that would crush any vessel long before reaching whatever core might exist at the center. Dr. David Stevenson, Caltech's leading expert on planetary interiors, described the revelation decades later. We realized Jupiter was less like Earth and more like a failed star. A ball of fluid with weather patterns larger than our entire planet. But Jupiter and Saturn, massive as they were, at least made theoretical sense. Their enormous gravity could hold hydrogen in liquid metallic states. The ice giants were supposed to be different. Smaller. Simpler. More like overgrown versions of Earth. Voyager 2 proved that assumption catastrophically wrong. When Voyager 2 flew past Uranus in 1986 and Neptune in 1989, it sent back data that puzzled scientists for years. Both planets radiated far more heat than they should. Neptune, despite being farther from the Sun, was actually warmer than Uranus. Their magnetic fields were bizarrely tilted, offset from their rotational axes by angles that made no geometric sense. Something strange was happening inside these worlds. Something the models could not explain. Dr. Heidi Hammel, a planetary astronomer who worked on the Voyager-Neptune encounter, remembers the confusion. The magnetic field data alone kept theorists arguing for a decade. Nothing we knew about planetary interiors could produce those readings. The answer, when it finally emerged, was more radical than anyone expected. Uranus and Neptune were not gas giants with solid cores. They were fluid giants, worlds where most of the interior existed in exotic liquid states that blurred the line between chemistry and physics. The water inside these planets was not water as you know it. At pressures exceeding 200,000 atmospheres, water molecules ionize. Oxygen and hydrogen atoms separate and flow independently, conducting electricity like liquid metal. Scientists call this state superionic water. It behaves like nothing on Earth, a crystal lattice of oxygen atoms with hydrogen ions streaming through it like a fluid. Solid and liquid simultaneously. This superionic ocean could explain the bizarre magnetic fields. It could explain the excess heat. And it suggested that the ice giants were far more complex and far more alien than anyone had imagined. But here was the complication that shattered existing theories. If Uranus and Neptune formed the way textbooks described, slowly accumulating ice and rock in the outer solar system, their interiors should look similar. Same composition. Same structure. Same heat output. They did not. Neptune radiates 2.6 times more energy than it receives from the Sun. Uranus radiates almost nothing. Two planets of nearly identical size, nearly identical composition, formed in the same region of the solar nebula, and one runs hot while the other runs cold. Dr. Mark Hofstadter, senior research scientist at NASA's Jet Propulsion Laboratory, calls it one of the most persistent mysteries in planetary science. We have proposed dozens of explanations over 30 years. None of them fully work. Some theorists suggest Uranus suffered a catastrophic collision that disrupted its internal heat flow. Others propose that its interior has stratified into layers that trap energy. A few radical models question whether the two planets formed in the same location at all. The mystery remains unsolved. And it carries enormous implications for understanding liquid worlds beyond our solar system. If we cannot explain the ice giants in our own backyard, how can we predict what sub-Neptunes around distant stars might look like inside? But no one expected what came next, when Kepler's data revealed that these strange, surfaceless worlds were not the exception, they were the rule. The Kepler Space Telescope launched in 2009 with a single mission: count how many planets orbit other stars. 4 years later, it had found thousands. And the numbers made no sense. Rocky planets like Earth were rare. Gas giants like Jupiter were uncommon. But in between, in a size range that does not exist in our solar system, Kepler found world after world after world. Planets between 1.7 and 3.5 Earth radii dominated the data. They appeared around nearly every type of star. Red dwarfs, sun-like yellow stars, even binary systems. The universe, it seemed, preferred making planets we had never seen before. Planetary scientists called them sub-Neptunes. But the name revealed how little we understood. We were defining alien worlds by what they were not quite Neptune, not quite Earth, not quite anything familiar. Dr. Leslie Rogers, an astrophysicist at the University of Chicago, published a study in 2015 that drew a line in the cosmic sand. Her analysis of Kepler data showed a sharp transition at 1.6 Earth radii. Below that threshold, planets were predominantly rocky. Above it, they required substantial volatile envelopes, thick atmospheres or deep liquid layers that dramatically lowered their average density. The implication stunned the planetary science community. Most sub-Neptunes could not be supersized versions of Earth. Their densities were too low. They had to contain enormous quantities of water, ammonia, hydrogen, or all three. Many of them, perhaps most of them, might be ocean worlds without end, but here was the factor that shattered existing knowledge. For decades, astronomers assumed that water worlds would look like Earth with deeper oceans. A rocky seafloor somewhere below. Hydrothermal vents pumping nutrients. Familiar chemistry, just scaled up. High-pressure physics destroyed that assumption. Dr. Li Zheng, a planetary interior modeler at Harvard, published simulations in 2019 that traced what happens to water under extreme compression. On a planet 5 times Earth's mass with 50% water content, the pressures at depth exceed anything in our experience. At around 1 million atmospheres, water transforms into exotic ice phases. Ice 7, Ice X, Ice 18, crystalline structures that form even at temperatures reaching thousands of degrees. This was not frozen water as you know it. These were high-pressure ice polymorphs, hot and dense, forming a solid mantle around the rocky core. Any ocean on such a world would float above this ice layer, completely isolated from the rock below. No seafloor. No hydrothermal vents. No mineral nutrients cycling into the water. Dr. Zheng's conclusion was stark: these worlds would have oceans hundreds of kilometers deep, but the water would never touch rock. The chemistry we assume is necessary for life, it might never happen. Everything we thought we knew about habitable oceans was wrong. The scientific community fractured into camps. Some researchers argued that life could find alternative energy sources. Radiation from the star. Chemical gradients within the water itself. Perhaps biology did not require the rock-water interface we see on Earth. Others pushed back hard. Dr. Stephen Desch, an astrophysicist at Arizona State University, published models suggesting that without mineral dissolution, ocean worlds would lack the phosphorus, sulfur, and iron that terrestrial biochemistry demands. These planets might be sterile by default, beautiful, vast, and utterly lifeless. A third group questioned whether sub-Neptunes were water worlds at all. Perhaps they were hydrogen-dominated, with thick primordial atmospheres surrounding rocky cores. Perhaps the low densities reflected gas, not liquid. The James Webb Space Telescope was built, in part, to settle this debate. In 2022, Webb turned toward a sub-Neptune called K2-18b, orbiting a red dwarf 48 light-years away. Early spectroscopic analysis detected methane and carbon dioxide in its atmosphere, but curiously little ammonia. Some researchers interpreted this as evidence for a liquid water ocean beneath hydrogen clouds. Others remained skeptical. The data allowed multiple interpretations. The planet might be a gas-shrouded halo world. It might be something stranger still. What everyone agreed on was this: we were witnessing a new category of planet, unlike anything in our solar system, and we barely understood the physics of what we were seeing. But the real question was not what these worlds were made of. The real question was whether anything could live there. The breakthrough came from an unexpected direction. Not from telescopes pointed at distant stars, but from laboratories simulating alien oceans here on Earth. In 2021, a team at the University of Nantes in France built a high-pressure chamber capable of recreating conditions inside sub-Neptune interiors. They subjected water-ammonia mixtures to pressures exceeding 40,000 atmospheres while heating them to 1500 degrees Celsius. What emerged challenged the assumption that hot ice layers would sterilize these worlds. Dr. Olivier Boulanger, the physicist leading the experiment, described the result: we expected a dead zone. Instead, we found chemistry. Complex chemistry. The interface between liquid water and high-pressure ice was not inert. It was reactive. Ions cycled between phases. Molecular structures formed and dissolved. The boundary layer behaved almost like a membrane, exchanging compounds between the ocean above and the exotic ice below. This single discovery reopened a door that high-pressure physics had seemingly closed. Perhaps water worlds did not need to touch rock. Perhaps the ice itself could provide the chemical gradients necessary for something like metabolism. Dr. Tessa Fisher, an astrobiologist at Arizona State University, published a theoretical follow-up exploring what life might look like on such a world. Without a seafloor, organisms could not anchor. They would drift perpetually in a three-dimensional liquid environment, never encountering solid surfaces. Evolution would favor buoyancy control over locomotion. Sensing pressure gradients over sensing light. We keep imagining alien life as modified Earth life, Fisher wrote. But ocean worlds force us to ask what biology looks like when there is no up and no down. When the entire biosphere floats. The threads began connecting. Neptune's diamond rain. Uranus's cold silence. The superionic water that defied solid and liquid categories. The sub-Neptunes that Kepler found by the thousands. The high-pressure ice experiments revealing unexpected chemistry. Each discovery had seemed like an isolated puzzle. Now planetary scientists started seeing the unified picture. Liquid worlds were not failed Earths. They were their own category of cosmic object, governed by physics that rarely operates on our planet. And they might be the most common type of habitable environment in the universe, if we expanded our definition of habitable. Dr. Nika Madhusudhan, the Cambridge astrophysicist who led the K2-18b analysis, articulated the shift. For decades, we searched for Earth twins. We looked for rocky planets with thin atmospheres and surface oceans. But the data tells us those worlds are rare. The common planets are the ones with no surface at all. If life exists elsewhere, it may exist primarily in forms we would barely recognize, floating in global oceans under crushing skies. The James Webb Space Telescope continued gathering spectra from sub-Neptune atmospheres. Each observation added constraints. Each constraint narrowed the possibilities. Carbon dioxide abundances suggested some worlds had water-rock interactions after all, perhaps during formation, before high-pressure ices sealed the cores away. Methane ratios hinted at chemical disequilibrium, the kind that biology or geology could produce. Nothing was confirmed. But nothing was ruled out either. Senior scientists who had spent careers studying planetary formation began reflecting on the larger implications. Dr. Jonathan Lunine, a planetary scientist at Cornell who has worked on missions from Cassini to Europa Clipper, offered a sobering perspective. We built our theories of planet formation around one solar system. One data point. Now we have thousands of data points, and they are telling us we were not wrong exactly, but profoundly incomplete. The solar system, it turns out, is the outlier. We have rocky inner planets and gas giants in the outer reaches, with nothing substantial in between. Most planetary systems fill that gap with sub-Neptunes, worlds that could hold more liquid water than all the rocky planets in our solar neighborhood combined. If water is the prerequisite for life, these liquid giants might be the primary reservoirs of habitability in the galaxy. But profound questions remained unanswered. How do these planets form? Why did our solar system skip this category entirely? Could complex chemistry in high-pressure oceans ever produce something we would call alive? The Decadal Survey, the document that guides NASA's priorities for 10-year cycles, now listed ice giant and sub-Neptune exploration as top-tier objectives. A dedicated mission to Uranus gained momentum. Future telescope concepts optimized for exoplanet atmospheres entered early design phases. The science was accelerating. But the real question was not what we had found. It was what it meant for our place in the cosmos. Step back for a moment. Consider what we have learned. The most common planets in our galaxy have no ground to stand on. They are spheres of liquid and gas, wrapped in crushing atmospheres, hiding oceans that dwarf anything on Earth by factors of thousands. Their interiors produce diamond rain and superionic ice. Their chemistry operates under conditions no human laboratory can sustain for more than fractions of a second. And they may contain more habitable volume than all the rocky worlds combined. This is not speculation. This is what the data shows. Dr. Sarah Seeger, who has spent 3 decades hunting for signs of life beyond Earth, frames the implication directly. We imagined finding life on a world like ours. A planet with continents and coastlines. But the universe seems to prefer something else entirely. If biology exists out there, it may spend its entire existence without ever encountering solid matter. The James Webb Space Telescope continues scanning sub-Neptune atmospheres, searching for chemical signatures that cannot be explained by geology alone. Future missions are already being designed. The Uranus orbiter and probe, recommended by the latest Decadal Survey, would spend years studying an ice giant up close, dropping an instrument package into that endless blue atmosphere to measure what no spacecraft has ever directly sampled. Beyond our solar system, next-generation observatories will push further. The Habitable Worlds Observatory, planned for the 2040s, aims to image Earth-sized exoplanets directly. But its instruments will also capture light from sub-Neptunes, refining our understanding of their atmospheric compositions, their cloud structures, their potential for harboring the chemistry of life. We are building the tools to answer questions that humanity has asked for millennia. And the answers may arrive within a generation. But the deeper implication is not scientific. It is philosophical. For all of human history, we have defined worlds by their surfaces. Mountains and valleys. Oceans and shores. Deserts and forests. Our mythologies placed underworlds beneath our feet and heavens above our heads. Our very concept of place depends on having somewhere to stand. Liquid planets dissolve that framework entirely. On a world with no surface, there is no horizon. No sunrise over solid ground. No footprints left behind. An organism born in such an ocean would never experience the boundary between water and air, between swimming and walking, between here and there. Its entire universe would be gradient, pressure increasing with depth, temperature shifting, chemistry evolving, but never a hard edge, never a final shore. Carl Sagan once wrote that astronomy is a humbling and character-building experience. He was describing the overview effect, the realization that Earth is a tiny pale blue dot in an incomprehensibly vast cosmos. But liquid worlds add another dimension to that humility. They suggest that even our concept of what a world is, what a home could be, reflects the accident of our origin rather than any universal truth. We evolved on a planet with a crust. And so we assumed all planets had crusts. We were wrong. Return now to where we began. Imagine falling through an atmosphere and never stopping. No surface rushing up to meet you. Just endless ocean, thickening around you, pressure mounting, light fading, until the water itself transforms into something that is neither solid nor liquid nor anything you have a name for. This is Neptune. This is Uranus. This is K2-18b and TOI 1452b and thousands of other worlds we have only begun to catalogue. And somewhere in those crushing depths, chemistry is happening. Molecules are forming and breaking. Energy is cycling through gradients and boundaries. Whether that chemistry ever crosses the threshold into biology, we do not yet know. But we are looking. For the first time in human history, we have the instruments to ask the question and the patience to wait for the answer. Dr. Nitka Madhusudhan captured it simply: we are not searching for Earth anymore. We are searching for life. And life may have found homes we never imagined. The universe is stranger than we assumed. It is also more generous. It builds worlds without floors, oceans without shores, possibilities without limits. 14 billion miles from where you sit, diamond rain is falling through an alien sea. 400 light-years away, a sub-Neptune orbits a quiet red star, its atmosphere thick with methane, its interior a mystery we are only beginning to probe. The cosmos is still calling. Will you keep listening?